the last lecture by Yana, and again it will be of 2 parts. Yes.
Yes.
From 2 parts. So we will have lecture, small break, and again we will finish with this.
Thank you. So since I keep on coughing, I will prefer not to use the microphone, but if you don't hear me, just say I will try to keep more loud. Okay. Yeah, so it was the original schedule of the lecture. So yesterday we have discussed as much as we could from lecture 3 and 4, and today we will discuss the lecture 5. But in an extended way, so that it will be 1 lecture and a half. So the last, this 5th part, 5th lecture, has the title Stochastic Processes and Evolution Equations in the Model of Anomalous Diffusion. So I skipped this long text because it was just the announcement of the summer school, just the same text. And I recall you the classical setting, which we have discussed all this week. So, sorry, in this lecture I have changed some notations because there will be more objects and not that many letters. That's why. So, some new people are coming. You should not be late. You have lost. You have missed the most important part of the lecture. Okay. So, we consider a time homogeneous Markov process. Now I denote it as big X. This Markov process means that it has no memory and hence it has transition property. That is a function p of between variables, p x dy, which describes the probability of transition from the point x to some set dy when we have t units of time for this transition. I recall you that if we have a Markov process, we have this transition kernel, and hence we can consider family of integral operators with this kernel. In one hand, by definition, taking this identity into account, this integral is nothing else but the expectation of u0 at xt, assuming that xt starts at x. On the other hand, taking into account Chapman-Kolmogorov equality equation for the transition probability, we obtain the semi-group property of this family of operators. So we have Markov process, hence we have its transition kernel, hence we have a family of, hence we have a semi-group of operators with this kernel. If this semi-group turns out, to be a strongly continuous semi-group on some reasonable bounded space, then it has generator, and then this semi-group solves the Cauchy problem for this evolution equation. So for any initial condition, for any initial condition from domain of operator, we obtain the classical solution. For all other initial conditions, or for any other elements of our bounded space, we obtain the so-called mild solution given by this formula. Mild solution meaning that it is not now C1 with respect to t, but still it is something which makes sense. Okay, so what is written here, this is just the integral form of this evolution equation. And in this lecture, this integral form will be more convenient for consideration. So this is my initial data, and so I just integrate this identity and use my initial data to calculate this integral. So here we have the integral from 0 to t, and then the right-hand side of this equation. Okay, so this is the classical setting, and we have discussed many interesting processes yesterday, particular failure processes, Levy processes, and also Levy subordinators. So they all fit to this setting. And so the basic pair here for this setting is, of course, Brownian motion and heat equation. So heat equation, it is the equation where my L, my generator, is 1/2 Laplacian, and the corresponding Markov process is Brownian motion. So the solution of heat equation has this stochastic representation in terms of Brownian motion. One also says that the heat equation is the governing equation for Brownian motion. That is, again, this connection is true, or moreover, one can show that transition probability of Brownian motion is the fundamental solution of this equation. So when we have this connection, we say that, this equation here is the governing equation for this process. And this process gives the stochastic solution in this form, the stochastic solution of this equation. This is just the terminology. Okay, so this couple heat equation of Brownian motion, they correspond to the so-called classical diffusion, which was explained by Einstein already more than a century ago. Well, not more than, I guess already more than a century ago. And this is what is understood as classical diffusion. So what are the main features of classical diffusion? So we consider particles which diffuse like in a liquid, many particles, and we can calculate the mean square displacement of the particles, so which we observe. And in the classical diffusion, this mean square displacement of the particles is proportional to the increment of time. So if we describe everything by a stochastic process, so mean square displacement corresponds to the variance of the process, and variance of Brownian motion is exactly t. So this is what is written here. Okay, and also another basic feature of the classical diffusion is that this underlying stochastic process is Gaussian. That is, this distribution decays very fast, not distribution, PDF of this distribution, the function, which doesn't have heavy tails, or distribution does not have heavy tails, yeah? So the PDF decays very fast when we go away from the mean. Yeah, so Gaussian law is like, again, something fundamental. Okay, but so this classical diffusion has been observed already starting from Brownian motion. But nowadays the measurement equipment is already developing more and more, and there are methods of the so-called single particle tracking. So when the scientists really can observe each particle, not each, but each marked particle. And it turns out that now there are many evidences that diffusion can be anomalous. What does mean anomalous diffusion? This means that the mean square displacement is not proportional to the increment of time anymore. That is, the diffusion really occurs qualitatively faster or slower than the classical one, and or the underlying stochastic processes have no Gaussian law. In particular, they may have heavy tails. Okay, so this is a small list of situations where this anomalous diffusion has been observed. So if the diffusion takes place qualitatively slower than the classical one, it is called subdiffusion. So I'm not going to discuss the whole list, and just say a few words about the first item. So it has been observed subdiffusion in many complex self-organized systems in biology, in particular when one considers motion of macromolecules in the cell, cytoplasm, and membrane. So one can understand it like a diffusion in a crowded medium. So there are a lot of obstacles. That's why the motion is slowed down. Yeah, and that's why it's probably natural to expect a kind of subdiffusion. On the other hand, there are also superdiffusion. So this is a diffusion which occurs qualitatively faster than the classical one. And again, there are many situations where one can observe such thing. So some of them, okay, so probably a few words. So subdiffusion, it can be understood as a diffusion in crowded media, or a diffusion in percolative and porous systems. Yeah, or something on some diffusion somewhere which has fractal structure. So this is, so to say, so some properties of the media which make everything slowly. And super diffusion, if you can look at the list, so there is the word turbulence. So turbulent diffusion, transport in turbulent plasma, special domains of rotating flows, but also completely different things like quantum optics and so on and so forth, and also diffusion research mechanisms. So what is meant here? For example, we have our immune system. So we have some cells of the immune system. And it turns out that their behavior is not quite like a diffusion. Namely, this antibodies, yeah, so cells of immune system. Antibodies which kill bats, viruses, and all of these things. So there are different types of them. So some types of them behave themselves as follows. So they come to some place in our blood and diffuse there for a while. So to say, they check the environment. So if everything is fine, no viruses, then they somehow like go far away, or make a jump, so to say. So go far away from this place to another place, and then diffuse there to check if everything is fine there. And then again make a big jump somewhere and check if everything is fine there. So it's like a searching mechanism. So diffusion plus big jumps. And this big, or directed, not like a random behavior, but like a searching mechanism. And then, so this speeds up the area visited by the particles, so to say. So if you consider it as a diffusion, you see that the particles spread faster. Okay, so there are many models. So there are many situations where one can observe something like a diffusion, but the speed of this diffusion or the underlying processes, they behave like anomalous diffusion. On the other hand, there are of course many approaches and many models how to describe this. So first of all, this is a small list of papers. They all are survey papers which present, and they all are written by physicians. So they just present what is what, introduce the subject and give a lot of references and a lot of information about where and what can be found. So as I said, there are many different models how to describe anomalous diffusion. And today I would like to discuss, first I would like to discuss one approach. And in terms of this approach, the basic equation for anomalous diffusion is the so-called time and space fractional heat equation. So for classical diffusion we have heat equation. Now we have something more general, which is called time and space fractional heat equation. So what is this fractional heat equation? On the right-hand side, Laplacian is replaced by fractional Laplacian. And the power is between 0 and 1. So if gamma is equal to 1, we just recover Laplacian. And on the left-hand side, instead of the first-ordered partial derivative of u, we have the so-called Caputa time fractional derivative of order beta. Beta is between 0 and 1, and again, if beta is equal to 1, we obtain just the first-order derivative, and hence we recover the heat equation. So, so as I already discussed yesterday and on Tuesday, this fractional Laplacian is the generator of a Markov process and even Levy process known as symmetric stable process. So the index of stability here would be 2 gamma, because we have the symbol of this process would be, so you see, the symbol would be p squared. So for Laplacian, okay, we can think about 1/2 also. And to the power gamma, so the symbol would be 2 gamma. So alpha stable would be the process for alpha equal to 2 gamma. So on the right hand side is something more or less known. So we still have operator which is a generator of a Markov process. But what does mean this left hand side? So the first statement is that the corresponding integral equation for this guy looks as follows. So I will define the Caputo fractional derivative in a minute, and I will show that it is exactly, so this equation corresponds to this equation, but nevertheless, just before looking at this equation. So for beta equal to 1, here we have power 0, so this term disappears. And we have just u is equal to u0 plus integral, and here stays mu ds. But if beta is not equal to 1, then we have this kernel, which depends on time, and we will call it memory kernel. You will see later on why we call it memory kernel. So in comparison with the classical case, when we have the first order time derivative, we have here some kernel which depends on time in this integral. Okay, so now let me clarify what is what here. What does mean Caputo time fractional derivative? So a small clarifying slide. So first of all, I will denote Laplace transform of a function by this symbol. So the symbol. So if I write ft and then this symbol f, which letter I use, p, this means that this is a function and this is the Laplace transform of this function. So this is just a short notation. So if we calculate Laplace transform of this power function, where q is just some parameter, it can be complex, but the real part is bigger than -1, then its Laplace transform is just gamma, Euler gamma function, and again power function of this power. So I don't know, so is Laplace transform known for you? Not. Please raise your hand who knows Laplace transform. 2. You know Laplace transform. Okay. So then this is an exercise to calculate it. It's very easy. But just this power function has its Laplace transform again given by power function. This is the connection between two powers. And also another property of Laplace transform is that if the Laplace transform of function small f is a function big F, then the Laplace transform of the derivative of the function f is given by this. That is again, the operation of differentiation is mapped into operation of multiplication with the variable. Yeah? But since we Laplace transform, I recall that so f of p here is just integral from 0 to infinity e to the power minus pt f of t dt. So since we integrate from 0 to infinity, not from minus infinity as in Fourier transform, then when we calculate the Laplace transform for the derivative, we just use integration by parts, and then a term at 0 will appear. And this is exactly what is written here. Doing integration by parts, we obtain this one. Okay. So these are the properties of Laplace transform, and exactly using the Laplace transform, we define the Caputo time fraction, the Caputo fractional derivative. So this is the definition: Caputo fractional derivative of order beta between 0 and 1 for good functions, so that all formulas make sense, is defined as follows. So the Laplace transform of Caputo fractional derivative of function f is p to the power beta multiplied with the Laplace transform of the original function f minus this term. Sorry, so again, so here p stays in the power which is 1 less than here. So if you put beta equal to 1, you exactly obtain the same formula. So it is actually very similar to what we have seen yesterday. Yesterday we have considered Fourier transform, and this power multiplication with the power of variable was a symbol of a fractional Laplacian. Yeah? So here the same, but now we are interested in derivative with respect to time. Time should be always non-negative, and that's why instead of Fourier transform we use Laplace transform. And that's why a new type of fractional derivative. But the idea is again that after this integral transform, differentiation is mapped into multiplication with a variable. So fractional differentiation corresponds to multiplication to the variable in this interesting power. Okay, so this is the definition of Caputo fractional derivative for good functions, of course, so that all makes sense. Now we consider this equality. Just again, assume we have good functions, and we consider this equality. That the Caputo fractional derivative of one function is equal to another function. So assume that this function g on the right-hand side has Laplace transform big G. So applying Laplace transform to this identity, on the left-hand side I have this. This is just definition of Caputo fractional derivative. And on the right-hand side I have this, big G. So then I divide everything on p to the power beta. If I divide the whole equality on p to the power beta, I obtain f of p minus f at 0 divide on p equal to p to the power minus beta times g of p. And now, so what I wanted to say you here, if I wanted to say something, well, actually I would. So let me see. So again, some properties of the Laplace transform is used. In particular, we know that the function, which is indicator function of interval from 1 to infinity of t, it's a Heaviside function, probably you know this, or step function. So its Laplace transform is just 1 over p. Okay. So so if I would like to apply, so to say, the inverse Laplace transform to this identity, what stays in the left-hand side? In the left-hand side stays ft minus this constant multiplied with the step function. So just 1, if we consider positive or negative t. Okay? And then what is the, if I would like to invert the Laplace transform of this thing? So p to the power minus b multiplied with g of p. So again, we use the property of the Laplace transform, that Laplace transform of a convolution of two functions is just product of Laplace transforms. So we have here product of two Laplace transforms. This is a Laplace transform of small g, and this is a Laplace transform of some function. So we use this property, and we see that this p to the power minus beta is the Laplace transform of the following function. I guess it is written here. Yeah. T to the power beta minus 1 divided on the constant gamma of beta. Okay? So when I invert this, so I apply inverse Laplace transform to this story. So this is just a Laplace transform of a convolution, and hence I have this convolution. Convolution of this function and this function. Is it clear how we have obtained this identity? Please raise your hand who has understood. Just using properties of Laplace transform and dividing on P and out to the power beta. Okay. So why I was doing that all? Just to show you that this identity, so if we have Caputo derivative on the left-hand side, so this is like a differential equation. This differential equation corresponds to this integral equation, where we have here function is equal to initial condition plus this integral operator. And now coming back to my statement, this is my time fractional heat equation with Caputo fractional derivative, and here the corresponding integral equation. This is just exactly what we have obtained. Yeah. So this is my G, assuming G is a good function. Okay, so this is the basic equation in this new setting of anomalous diffusion. but how to persuade you that it is really so? So as I said, there are many approaches to describe anomalous diffusion. And today I would like to discuss one particular approach, which is one historically probably the first one and the most established one. It is the so-called continuous time random walks, CTRW, CTRW, continuous time random walks. So it turns out that this equation is a governing equation of processes which pop up as scaling limits of this type of random walks. Probably you know that if you consider just the Bernoulli random walk, just ordinary random walk, that is a particle stays at zero, so we have deterministic time steps, and at each time step the particle make jumps of a particular size. But the direction of this step is random. So in one-dimensional case, we have only two options, up and down, same with equal probability. Then it's a Bernoulli random walk. So particle goes like up, then the next step it goes again up, for example. Then the next step it goes down, for example, down, 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 and so on. So this is like a Bernoulli random walk. And rescaling such random walk. So I can describe this random walk as a sum of random variables, psi I, where these random variables are just Bernoulli random variables taking values plus or minus 1. And then we can use, like, roughly speaking, central limit theorem to say that in the limit when t tends to infinity, when n tends to infinity, we have a standard normal distribution if we rescale it properly. Yeah? So the functional analog of the central limit theorem says that even the whole path of random walk after rescaling converge to the path of Brownian motion. Yeah? So, natural replacement of standard normal Gaussian distribution, if we consider the whole path from 0 to something, yeah, it is Brownian motion. Okay, so now we consider something more advanced, namely not just the Bernoulli random walk, but a continuous time random walk. What is it? It is a random walk with jumps of random length, so not 1 or minus 1, but with random length. So jumps have some distribution. And between jumps, there is not a deterministic time, but some random time, waiting time. So a particle waits some random time, and then jumps, and the size of jump is a random variable. Then again weight, and then again jump. So if jumps are very big, can be big, then it's natural to expect that the limiting diffusion process will be a super diffusion. Yeah? So if particles may jump may produce very big jumps, so it will go away faster than the classical particle, ordinary particle. Yeah? On the other hand, if the waiting times are big, yeah, then everything will be slowed down. So it seems to be a natural model for anomalous diffusion. So playing with, making waiting times big, we can slow down the diffusion. Making jumps big, we can speed up the diffusion. So we can play with two these factors to obtain what we want. Okay. So this is the model of continuous time random walk. So how we describe it. So we have a family of random IID random variables which describe our jumps. So we assume that all jumps are IID, that is, they are independent and have the same distribution. Also we have a family of IID random variables which are non-negative, and they describe waiting times between jumps. Again, they have the same distribution. So in the simplest case, we consider the so-called uncoupled random walk. Namely, we mean that the jumps do not depend on waiting time. So then how we describe this path of this random walking? So first of all, the time of the nth jump number n, is described by a random variable t of n, which is just the sum of first n waiting times. Agree? And t of 0 is defined to be 0. Then position after the nth jump is just the sum of first n jumps. So we start at 0, and then each jump gives something to our position. Yeah? So position after the nth jump is just the sum of first n jumps. S of 0 is defined to be 0. Then, now I'm interested, so now my time is continuous, t, and I'm interested in what's going on to the time moment t. So number of jumps which have occurred up to time t is defined in this way. So how many jumps has happened up to time t? So we just calculate the waiting times, and we take as many waiting times as possible to have still the time of the last jump is smaller in quantity. So I'm drinking and you are thinking about the definition. So it is clear why the number of jumps up to time t has this form. Okay. So please note that this definition gives us a kind of inverse process to the process t. Not process, okay. Process, nevertheless process. So at nt is something like inverse to this guy. Moreover, if my waiting times have exponential distribution, then what is staying here is just a definition of the Poisson process. So this is usually discussed in the course of stochastic processes, standard course. If you know, okay. If you don't know, don't worry. This is just a kind of remark. But so if my waiting times are exponential, then this guy is just a Poisson process. Now, what is the position of the particle at time t? It is just the amount of jumps occurred up to time t. And how many jumps occurred at time t is given by this random variable. So we have this composition. Yeah? Yeah. So position at time t is given as S of mt. That is the sum of jumps. But how many jumps we have to take? It is a random number, which depends on waiting time. So if my waiting times have exponential distribution, then this is a Poisson process, and what stays here is known as compound Poisson process. And this is a Markov process. But if my waiting times do not have exponential distribution, we call that exponential distribution has no memory. Yeah? This is a property of this distribution, which allows to construct here a Markov process. Bless you. But if my waiting times have some another distribution, not exponential, then this guy here is no more Markov process. Just a small remark. Okay, so this is our stochastic process, our continuous time random walk, which we are interested in. So the position of the particle is described by this type of process. Now, let psi be a probability density function of my waiting times, and lambda be a probability density function of the jumps. And we assume that this lambda is a symmetric function, so that all directions, so it does not depend on the direction, but on the radius only. So all directions are equipossible uniformly with the same probability, so to say. Yeah, like here, the particle may go up with the same probability as it goes down. So here everything happens in RD, I have forgotten to tell you. So we have more possibilities to jump, but we take a distribution which is symmetric with respect to 0. So my probability density function only depends on radius, so distance from the 0. Okay, so consider mean waiting time and consider jump length variance. So these are two features of the system. So it turns out that there exists exactly 4 regimes of continuous time random walks. If my mean waiting time is finite and jump length variance is finite, we have a standard diffusion. These two conditions mean that waiting times are small enough and jumps are small enough, so substantially nothing has changed. We still are in the standard diffusion. If my waiting times are small enough, but my jumps are big enough, then I have super diffusion. If my waiting times are big enough, but jumps length is small enough, my jumps are small enough, then we have subdiffusion. So this can be understood as like we have sticking effects or trapping effects for the particles. So trapping makes sense if we consider like a porous media or like fractal media, and sticking also when we have like a diffusion in a crowded media, and the obstacles may make the particles stick to them and not move further. Okay, and if both things are big, that is, my waiting times are big and jump length variance is big, then we have so-called general anomalous diffusion or fractional diffusion. It may happen that okay, the waiting times compensate the jumps, so diffusion occurs like with the same speed as the classical one, but nevertheless it is anomalous in the sense that the underlying processes are no more Gaussian. So there are heavy tails behind. I have just started, so don't worry, I will clarify all this. No, not all this, but many things. So let us investigate all these homologies. So the first result obtained by Monroe and Weiss many years ago is the following: that the probability density function Ptx, probability density function of finding the particle in the position x at time t, satisfies the following Monroe-Weiss equation. So position of particle is x at time t does not mean that we jump exactly at x at time t. It means that we may arrive at x earlier and stay there up to time t. Okay, now there is this equation. It is written as in the physical literature. You see this delta function. It's a generalized Dirac delta function. There is the rigorous mathematical equation and the corresponding calculations are given in this paper, but the rigorous version looks not that informative as the physical one, so to say. So I like this version. So this is a kind of equation where all guys are generalized functions. So I say probability density function, but it is of course a discrete probability density function. Okay, so the statement is that this probability density function, in the case of continuous time random walk, satisfies this equation. We are not going to prove this, but I will clarify you why this equation. What does mean all this equation? So I will clarify by means of the picture. So Ptx describes the probability that my particle is at point x at time t. But how to arrive there at x up to time t? So if x is just 0, there are two possibilities. The particle jumps, and then arrives at 0. And another possibility is that particle, recall that we start at 0 always. So the particle just stays at 0 all the time, yeah, up to t. And the particle is at 0. So this second possibility fits only for x equal to 0. For all other points, x, we really have to jump in order to get there. Agree? Okay, so this second possibility, just not to jump at all and stay in the 0, is described by this term. So delta of x signalizes us that we take into account this summand only if x equal to 0. And what is written here? So recall that C is the probability density function of our waiting times. So the probability that my first waiting time is bigger than t means that the particle stays lying without any jumps up to time t. Yes? But this is 1 minus probability that the particle, that g1 is smaller or equal to t. But this is 1 minus integral from 0 to t, Cs ds. Yes? And this one is just integral from 0 to infinity, Cs ds, because c is the PDF of a non-negative random variable, minus integral from 0 to t, c of s ds. So this difference gives us integral from t to infinity. Survival probability, and this is exactly what is written here. So the probability that the particle, so the probability that the first waiting time is bigger than t. Okay, so this is the meaning of this summand. And the second summand is the probability to arrive at point x by making jumps. So this term, also this possibility fits for all x equal to 0, x not equal to 0, And so let us understand what is written here in this remark. So the particle starts at 0, and after some jumps, the particle arrives at x. So at x, and then stays there up to time t. So there should be the last, so I don't know how many jumps this particle has made, but there should be the last jump into x. Yeah? So this means that somewhere this last jump will be made. This last jump will be made in some time moment theta, which lies between 0 and t. And this and particle will be somewhere in some point psi, from which it will jump into x. Okay? So what is written here in the integrand? So this is the probability that at time point theta, the particle is in the position psi. So this p. Then this is, so to say, corresponds to the ability to make jump from psi to x. And this is the probability that there will be no jumps in the time interval from theta to t. So we assume that all jumps and waiting times are independent. That's why we have a product here. But now, of course, this theta may be anything between 0 and t, and this psi may be anything in our space. That's why we have to integrate with respect to theta from 0 to t, and with respect to psi over the whole space. Okay? So this is the idea of why this equation was created, so to say. Now let us solve it. Namely, we are interested in the limits of continuous time random walk in the same way as the limit of ordinary Bernoulli random walk leads to Brownian motion. We want to consider the properly scaled probably limit of continuous time random walk. So let us work with this equation. So again, Laplace transform and Fourier transform. So this is the equation, and we would like to consider the Laplace transform with respect to time variable and the Fourier transform with respect to space variable of all this story. So let big P hat will be this double Laplace Fourier transform. Then let psi t has psi t have a Laplace transform psi p, or here I have u. Yeah, this is u. So psi has Laplace transform big psi, and lambda has a Fourier transform lambda hat. These are the definition. Then recall that Laplace transform of a convolution is a product of Laplace transform, and Fourier transform of convolution is a product of Fourier transform. Now I can use a Fourier transform with another normalization, so without this constant, not to play with constants. So this term will be transformed after applying Laplace and Fourier transform. What do we have here? So on the left-hand side we have p hat of which variables? U, y. On the right-hand side. So this convolution will be transformed into product p u y multiplied with lambda hat of y and with big psi of u plus, and then the second term. Recall that Dirac delta of x, we take Fourier transform and we obtain constant 1. So here I take Fourier transform without the normalization. y minus I y x f of x dx. So now without the constant, just to avoid constants everywhere. Huh? No, here should be y. Yeah. Taking into account my notations. So after applying the delta function, we obtain 1. And then we have to make a Laplace transform of this integral. And again, I use the properties of Laplace transform. If you know them, good. If you don't know, just you have a chance to know them. So if a function has Laplace, psi has Laplace transform of psi, then the function integral from 0 to t, psi s ds, has Laplace transform psi u divided over u. And then the function, this one, this is exactly this function, yeah? Recall that 1, this is just the indicator of the interval from 0 to 0. The hand-side function, and its Laplace transform is 1 over, now we have to do the so so here we should have, what should we have? 1 minus psi of u divided over u. And now if we put this to the left-hand side, so here would be equal to, and divide everything on psi, we obtain what is written here. Okay? Agree? I'm not lying. Everything is as it should be. Okay. Now, as I said, we are interested in the long-time behavior of my random walk, and actually what happens when then my particle goes away and away from 0. But it is what we are interested in terms of variables t and x. I feel the shock. Breathe some fresh air. So after we apply Fourier Laplace transform, we are now in the variables u and y. So the asymptotic when t and the norm of x tends to infinity corresponds to the asymptotic y and norm u tends to 0. I do not prove it, do not verify it, but there is a theorem, Harding-Tauberian theorem, which states that it is so. So we are interested in this equation, in solving this equation under this condition. So we may simplify this all. Yeah, just using considering everything in the neighborhood of 0. So let us consider an example of standard diffusion. So just an example. So as the probability density function of my waiting time, I take exponential waiting time. Then the first moment exists, is finite, and as the distribution of my jumps, I take just Gaussian distribution. Then the variance is finite. And hence, this is what I call regime number 1, standard diffusion. Okay, so if I have such psi, then I can calculate its Laplace transform explicitly. You can open any table, a standard table of Laplace transforms, and you will see that the Laplace transform of this function is just given by this function. So if I consider asymptotic around 0, so this function, so this is like a Taylor expansion of this function. So these are the first two terms of the Taylor expansion, around 0. Now I also can calculate the Fourier transform of this lambda explicitly. It is just e to the power minus, what are the notations? E to the power minus sigma quadrat norm sigma square norm y square. And again, using Taylor expansion of this function, this is the asymptotic when normal y tends to 0. So I just insert these asymptotics in this my equation written here. So what do I obtain? So first of all, 1 over psi u is exactly this thing. So let me just calculate it. So I have this equation above. So 1 over psi u is just 1 plus au multiplied with p hat minus, instead of lambda hat, I insert the asymptotic 1 minus sigma square y square p hat is equal to, and then here I use asymptotic, so for psi I use this asymptotic, so 1 minus 1 plus au will give me au. Then I divide it over u, and I have this asymptotic for 1 over psi, so this one. But in this case, I can forget about this and take only this leading term. I guess it is how it was done. So multiply, okay, 1 plus au, but I guess we can kill this au and keep only 1. So you see, 1 p hat minus 1 p hat, they will disappear, and what stays? Au p hat plus sigma square norm y square p hat is equal to a. I guess so, yeah. And then if we divide with a, then we have this equation. Yeah, it is written here. It is exactly what is written here with some new constant. And then if you apply Fourier Laplace transform inverse, if you invert our double Fourier Laplace transform, we obtain exactly this equation. Because one, this is the Fourier transform of delta x, and the Laplace transform of delta of t. So you see, this is the heat equation. Recall that everything is written in generalized functions. So this is says that pt, so this function p, small p of tx, solves the heat equation with this initial condition. Sorry. So this identity means that small p is the fundamental solution of the heat equation. So you see, we started from continuous time running walk, and in the particular case, for the particular type of regime, we have obtained just the heat equation. Now we do the same in another regime, a fractional regime, anomalous diffusion, regime number 4. So we take probability density functions psi and lambda with heavy tails. So we assume that the tails for the distribution of waiting times is like this power function, and the tails for the distributions of jump is like this power function. Then one can show in a similar way as we have done here that these functions, 1 over big psi and lambda, they have the following asymptotics. And then if we insert this asymptotic here in this equation, then we obtain this equation. Okay? And from this equation in particular, we can find p hat. It looks as follows. Please remember that we can find p hat, and it looks as follows. We will recall about that in a few minutes. But just looking at this equation, if we invert the Fourier Laplace transform, then here we have a symbol of fractional Laplacian. This is what is written here. Here we have not the Caputo fractional derivative, but its weak version, so the Caputo fractional derivative which works on generalized functions. So we forget about the initial conditions. So this is the Laplace transform of the generalized Caputo type fractional derivative. And then this function is the power function. Its Laplace transform looks as follows. And then it is this function of u times a function of y, and this function of y is an identically one, constant. So after inverting the Fourier transform, we obtain Dirac delta. So we have this equation, but just combining these two terms, this term and this term, this means that this is the same as the equation with, so to say, not generalized, but just ordinary Caputo fractional derivative and initial condition derivative. Okay, so just having the continuous time random walk, having its governing equation, which is a Monroe-Weiss equation, assuming, so making some assumptions on the distributions of waiting times and jumps, we see that in the limit, in the proper limit, the governing equation turns out to be this time and space fractional heat equation. Okay? So this all was just to persuade you that this is really the equation which is somehow related to continuous time random walk. And continuous time random walk seems to be a reasonable model for anomalous diffusion. Okay, now we skip some things, but I just want to say here that you know central limit theorem, that under some conditions the sum of IID random variables converges to standard normal distribution. Under some other conditions, a sum of IID random variables, okay, scaled probably, converges to something else. And the statement is that if we consider such type of limits for IID random variables, then all possible distributions which pop up in the limit, they are stable distributions. So actually all stable distributions may work as attractors, yeah, as limit distributions for sums of IID. And having some assumptions on the distribution of each summand in the sum, one specifies what kind of stability we have in the limit. What is the limit? So now what do we have here? In the regime of anomalous diffusion, the tails of waiting times are heavy. They are power function of this type. The tails of distribution of jumps, they also are heavy tails, and they are proportional to this power function. And recall that we have jumps. Jumps are IID random variables, and we have waiting times. They are also IID random variables. Recall that the time of the nth jump is just the sum of IID random variables. And position after the nth jump is also the sum of IID random variables. So under such conditions on the distributions, we also may do like a central limit theorem, but the corresponding convergence will be not to a Gaussian, not to a standard normal, but to the corresponding stable distribution with the corresponding index of stability. And so here, since all y have a symmetric distribution, in the limit we obtain symmetric alpha stable distribution. And in this case, all my waiting times were non-negative. So in the limit, after proper scaling, we obtain the stable distribution with index beta, but concentrated, a non-negative random variable which is still stable. This is a distribution So when we have considered beta stable subordinator, yeah, a family of measures. So these are exactly better. These measures are exactly beta stable distributions, which are concentrated only on one side. Yeah. So probably I'm speaking too fast, but the idea is that the objects which are related to TRW, yeah, to continuous time random walks, they are naturally lead in the limit to some stable distributions. Okay? So this sum will give rise to a beta stable subordinator, and this sum will give rise to symmetric alpha stable process. But, so we will see it in a minute, but this guy here, it is kind of inverse to this guy. So if this guy, in some sense, converges to beta stable distribution, then this guy kind of converges to inverse process to beta stable subordinator. And now it has been shown in this year, 2008, that so exactly as I said, that the properly rescaled sum of waiting times converges to a beta stable subordinator. Now my eta means the process, not the measure, but the process itself. And hence the rescaled inverse process converges to inverse process to the inverse to the beta stable subordinator. And then and also the rescaled sum of jumps converges to alpha stable Levy process, symmetric alpha stable Levy process. And hence the rescaled random walk, continuous time symmetric random walk, recall that X is a kind of composition, S and N. So S, rescaled S converges to alpha stable symmetric process, and N converges to inverse beta stable subordinator. Then this rescaled composition converges to a process which is just time change process. So it's a process which is a limit of Y's, so symmetric alpha stable process, time changed by inverse process of symmetric of beta stable subordinator. Of course, I do not prove anything. Convergence is a big convergence in a proper Skorokhod space, but nevertheless, so the conclusion is, so we consider continuous time random walks. It's so each of them seems to be a reasonable model for anomalous diffusion, and then if we consider a proper scaling limits of such processes, we obtain again a kind of subordination. Everything is used. So, summary. I have explained you that it is interesting to consider diffusions which have like sticking and tracking effects and have effects of large jumps. A reasonable model for that could be continuous time random walk. If we consider some scaling limits of random walks in the language of stochastics, then we obtain the following processes. We take a process which is a alpha stable symmetric Levy process, time changed by inverse subordinator. So I can write down like this. On the other hand, if I consider the scaling limit on the language of analysis, I obtain that the governing equation of continuous time random walk converges, in some sense, to the time and space fractional heat equation. Moreover, so this would be the last word in this setting. So this is the scaling limit of my continuous time random walk in this regime number 4. So if I consider the probability density function of this process, I can calculate it. Or better, if I consider the probability density function of this process, I can calculate its Fourier Laplace transform with respect to time and space. And I will obtain the function which we have already seen. It is exactly this p hat which solves the fractional heat equation, time and space fractional heat equation. So one can check really that this process has this equation as a governing equation. Okay, so analysis and stochastic have coincided. That is, considering scaling limits of processes gives us this guy. Considering this Laplace Fourier of Monroe-Weiss equation gives us fractional heat equation. But finally, this object, its probability density, its distribution, solves the fractional heat equation. Okay, I guess, yeah. That's all before the break. Now we have a break. It was an introduction. Now, after the break, we will have a lecture. It's a joke.